Chapter 2, Part 3, Molecules, Ions, and Compounds. So in here, we're going to start to talk about different types of molecules and what this means. So elements aren't often found alone. So we have 118 elements right now, and so they create molecules and compounds. So we usually find oxygen in nature as O2. And so this subscript tells you how many. So this says that there are 2 oxygens. Comparatively, if we have O3, this means that there are 3 oxygen atoms together. Later in the semester, we'll talk about what that looks like structurally, but today we're going to figure out what that is. And so that we will come across different types of molecules. We're going to see molecules. We're going to see ionic compounds. And so we're going to see molecules, ionic compounds, molecular compounds, and other things as we start to talk about that this semester. So there are a couple of different types of formulas that we're going to talk about for a compound. So the first one is the molecular formula. So a molecular formula is exactly how many atoms are found in the molecule. So this tells you who is at the party. Are there 5 hydrogens and 5 carbons? Are there 7 hydrogens and 52 carbons? Neither of those molecules exist, but that's an example. So a molecular formula tells you exactly how many atoms are found in the compound. So you have 2 hydrogens and an oxygen, that's water. If we were to have 2 carbons and 4 hydrogens, that is also a molecular formula. So the next formula we're going to look at is the empirical formula. This is the smallest whole number ratio of the atoms present. So if we look at the examples above, for H2O, the empirical formula is exactly the same. It's still H2O. For C2H4, the empirical formula is actually CH2. So it tells you that the base unit is 1 carbon and 2 hydrogens. So this doesn't make a lot of sense when we think about carbon molecules, but if we think about ionic compounds, which are things like sodium chloride, so sodium, let's say in this compound there are 761 sodiums for 761 chlorines. That's a lot of components, but we could simplify that to just be sodium chloride. So overall, 1 sodium interacts with 1 chlorine, but oftentimes we find that in a group of sodiums and a group of chlorines. So the last thing we can think about is a structural formula. So if we think about a component, so we're going to think about a molecule called methane, CH4. So this is the chemical formula. And then we could actually draw that as CH4. So this is in 2 dimensions. In 3 dimensions, it would look something like this. This is a 3D structure. And so there are other more graphic designs that you could find in your textbook or online that look a little bit more like ball and sticks, or you could have a 3D spherical structure. But the structural formula just tells you the arrangement of the atoms. So this is the arrangement of the atoms in 3D space. So we will learn how to make a structural formula and how to read those later on this semester. So what is the empirical formula for both of these molecules? So if we look at glucose and nitrous oxide, so for glucose, we can see that there's a base unit of 6. So we have carbon, hydrogen, 2, and O. Because 6 divided by 6 is 1, 12 divided by 6 is 2. So nitrous oxide, the empirical formula is just the same. And so that's always an acceptable answer. So I talked about how we could make ionic compounds. So before we talk about the ions, an ionic compound is formed when 2 ions interact. And we're going to study a lot of ionic compounds this semester. These are usually, if not always, a metal and a nonmetal. We'll talk about when they're not metals and nonmetals, but we need to figure out what the ions are. So it turns out that there are 2 types of ions. And so these are the anions. And so anions, these are going to be negative ions. So a negative ion is created when an element acquires an extra electron. So let's look at chlorine. So chlorine has 17 protons and 17 electrons. And this charge is 0. So, but if we think about chlorine minus, so it's added an now has a negative charge, it's going to keep the number of protons. It's going to gain an electron. So it's -1. So in this case, our anions, so the N here, I like to, when I think about it, it helps me remember that it's negative. And these are negative ions, or anions. So the other type is cation. So this has a T in it. So cations are positive ions. These are created by losing an electron. And so you'll notice that neither of these are affecting their protons. The protons, remember, are buried in the nucleus, and so they don't come and go. So a cation, if we were to think about sodium, it has 11 protons and 11 electrons, and that makes it neutral. When we think about sodium plus, we then think about how it has 11 protons and just 10 electrons, which is going to give it an overall +1 charge. And so the positive ions are considered cations. I remember that by looking at the T in the middle. So you might be wondering, so like, how do we know what the charge on the ion is? So sometimes we can figure that out, and sometimes we can read it off the periodic table. So if we look at our periodic table, I'm going to draw a picture of it. I'm going to ignore the lanthanide-actinide series for a little while. They are a little bit different. So all of our ions want to achieve noble gas configuration. So our noble gas is out here. And so these are group 8. So noble gas configurations, we'll talk a lot more about what that means in terms of number of electrons and other types of that in chapter 6. But for now, we know that they want to achieve that. If you know what it means to achieve octet, that's okay. So we can predict the charge on an electron. It turns out that it's a pattern based on location in the periodic table. So elements in this first row here want to be +1. Here, they prefer to be +2. We have +3. So we're going to skip our noble gases over here. And then we have a -1, -2, -3. Here you could have +4 or you could have -4. So the charge on an ion, so if we were to look here, we have oxygen, sulfur, selenium. All 3 of these prefer to acquire 2 extra electrons. When they become an ion, that's what we see. So all of the elements that we can see in these components follow these rules. Now what happens when we start to look in this part right here? These are the transition metals. And fortunately or unfortunately, I like to think of them as the no rules kids. So transition metals have the ability to lose different numbers of electrons. So for copper, we can have copper plus, and we can have copper 2 plus. So in this case, copper could be either copper 1 or copper +1 or copper +2. So when we think about the transition metals, this information can be provided for us. You can write it out as copper, open parentheses, Roman numeral 1. This tells you that we have a copper with a +1 charge on it. Or if you were to have copper in a compound, an ionic compound, we could back calculate that using the other component. We're going to talk about that in just a second. But overall, when we look at the periodic table, you can calculate the ionic state or the charge on any ion based on where it is located in the periodic table. So forming a compound. So an ionic compound is an anion, it's a cation interacting with an anion. Cations are often metals. Anions are usually nonmetals. We read these components left to right somewhat across the periodic table. And so when these interact with one another, we can start to look at how they interact. So what we want is they should be neutral. So the charge on the anion needs to equal the charge on the cation. Now, you might be thinking, but what if one is -2 and one is -1? So if you have a -2 charge and a +1 charge, that would mean that you need to have 2 of these. So you'd have a -2 interacting with a +1 and a +1. So that's what we're going to see when we start to make these compounds. So if we look at this table, we have elements on the left side, And then we're going to think about what is the cation and what is the anion charge, and then we're going to create the ionic formula. So if we look at our periodic table, we can see that sodium wants to be Na+. Chlorine wants to be Cl-. So you have a single positive charge and a single negative charge, so the ionic formula is going to be NaCl. So that's pretty simple. We've all heard of sodium chloride before. But what about aluminum and oxygen? So aluminum, based on its location, wants to be +3. And oxygen wants to be O2-. Okay, so now they don't fit together in a 1-to-1. But we need to find a way to where the number of aluminum ions and the number of oxygen ions comes together to create a neutral molecule. So if we had 2 aluminums, that would give us a +6. And we could have 3 oxygens, and that would give us a -6. And that would create a neutral species. So Al2O3 is this ionic formula. So let's look at magnesium and nitrogen. So Mg2+, and nitrogen is a 3-. Okay, so this is somewhat similar to what we see at the top in the row before, except now there will be 3 magnesiums and 2 nitrogens. So the more of these examples you do, the easier it will be. So let's look at calcium, Ca2+, and iodine, I-. Okay, well, there's 2 positives and 1 negative, so we're going to need a second iodine molecule. So we have CaI2. So it's important to note that in this case, all of these are single elements, and so we can just add a subscript directly underneath. So naming ionic compounds. We name them left to right. Usually metal to non-metal. Always cation to anion. So when we think about naming ionic compounds, so if we think about some of the ones we encountered on the last slide, we have NaCl. So we would name that sodium chloride. And so when we think about these, we're going to encounter them in this way. So when we have single elements, we look at them this way. Now, sometimes we're going to see a lot of things called polyatomics. So polyatomic ions are compounds that have multiple elements together. So these are things like nitrate, NO3-, sulfate, SO4 2-. So this is our nitrate ion. This is the sulfate. So the polyatomic ions can replace some of the, in this case, anions that we've met already. So when we name those, if we were to come up to NaNO3, we would name this sodium nitrate. So these names are part of the chemical name. So there is a handout called Common Ion Table. You are responsible for knowing all of those, the spelling and the charges. And there are about 35 on there. So you need to know all of those. So in that case, we can start to name our ionic components in this way. If we had, let's just say, lead 3 nitrate, we would know that that would be Pb NO3 3, because nitrate has a single charge on it, and this Roman numeral 3 tells us that the lead has a 3+ charge on it. So the last thing we're going to talk about are some simple organic compounds. So organic compounds are molecules that we come in contact with often. They are composed of carbons, nitrogens, occasionally, hydrogens, oxygens. So what makes these a little bit more interesting in some cases is that they are compounds created from nonmetals. So you're going to have elements that were typically already anions functioning as a cation. So we're going to look at some of these, but we really want to be able to know and name 8 of them. So first we're going to look at the alkanes, and then we're going to look at the alcohols. So the first one we're going to meet is CH4, and that's methane. When methane turns into an alcohol, we get CH3OH, and that's methanol. The next one we want to learn is C2H6, which is ethane. When ethane gets an alcohol group on it, we get C2H5OH, and this is ethanol. So propane, C3H8, can become C3H7OH. And that is propanol. So the last 2 we want to look at are C4H10, butane, and C4H9OH, which is butanol. So you need to be able to know these. You want to be able to know the name and the chemical formula for these alkenes and alcohols. These are simple organic molecules, and we will encounter them often. So you need to memorize the common ion table and these simple organic molecules.